So in this second video, I'm going to talk about the Adobe original neural network architecture. Then in the later videos, I'm going to propose my proposed changes for the project. So as mentioned in the previous video, Adobe starts out with gets as input W by H by 3 images. That's a color image of W height, weight, width, H height, and 3 color channels. Then the first 10 layers are convolutional layers from VGG19. So we take the original authors took the first 10 layers from VGG19 and used it in here, and then 2 extra convolutional layers are added in this block. They are mainly added for adding more nonlinearity and also downsampling the channel number. So at the end of the first block in here, we end up with 512 channels. Then in these two convolutional neural networks, it downsamples that size. It first converts it from 512 to 256 channel, then from 256 to 138 channels. Eventually, in here at this point, we end up with image feature size of W by 8, H by 8, or times 128. So in other words, we get 128 images, each of size W by 8, H by 8 size. Now these image features are then used in these two cascade chains, as I mentioned previously. These two cascade chains, cascade number 1, which is used for calculating belief maps, and chain number 2, for which is used for calculating affinity maps. Now I'm going to mainly talk about this section of network architecture. So let's focus. I will jump around in between both the cascades, both the cascade chains, because they are interconnected, as you can see in here in green and blue, green, red, and blue. So let's talk about the first cascade for the belief map. So the first belief map cascade in here gets as input the image features, again of size 128 channels in here. Zoom it out a little bit. Okay, so then it calculates, after getting the input, it calculates 9 belief maps, same as this one. So these 9 belief maps will also have W by 8, H by 8 by 9 size in here. And similarly, same goes for the second chain. It for calculating affinity maps, it gets as input the 128 channel image features, and then it calculates 16 affinity maps, each of size W by 8, H by 8 size, just like in here. So in the second stage, after this one, after this line that I drew towards this direction, in the cascade 2 for the belief map chain, it gets as input, just like this first chain, it gets as input the image features, then it gets to extra input, which are the belief maps calculated previously and the affinity maps calculated previously. So in short, it is getting 153 channel input, 128 coming from the image features in here, 9 channels coming from the previously calculated belief maps, and 16 channels coming from the previously calculated affinity maps. As a result, now it not only has the original image features, but also it has the previous predictions made by the neural network. As a result, it comes up with better estimation in these 9 belief maps. So it again outputs 9 belief maps, but these are usually better than the previously estimated belief maps. Same goes in the chain number 2, or affinity map chain. Cascade 2 in here, just like cascade 2 for belief maps, gets as input the 128 channels of image features. It gets the previously calculated belief maps and previously calculated affinity maps, as shown in here, red and green. As a result, it gets in total 153 channel input, and it produces 16 affinity maps. We just draw that with red. Okay, it gets 16 affinity maps, produces 16 affinity maps. And same thing goes for all of the later cascades in these chains. Every one of them gets 153 channels, that is 128 channels from the original input features and the previous detections or previous predictions by the neural network, both in terms of belief maps and affinity maps. So in this way, we finally end up with we finally end up with 9 belief maps, and we end up with 16 affinity maps. But so this is how this neural network architecture works. But one thing I want to focus is on loss calculation. So as mentioned in the previous video, that we are calculating belief maps that sort of looks like this, or in better would be look like this. So this would be the ground truth for belief maps. So the predictions that we will get, we will find out the pixel-wise difference between my ground truth and my predicted belief maps, and from there we will calculate the loss. Same thing goes for the affinity maps, and then we will use that loss to optimize my neural network architecture. But these are not the only belief maps we will be using. We will be actually monitoring in the loss function. Let me draw that with different okay, let's use this for belief maps. We'll be monitoring this part, this. So every output from every cascade will be included in the loss function. I will be penalizing the network if it can't estimate the belief maps perfectly starting from cascade 1. Then again in cascade 2, if it fails to predict perfect belief maps, the ones that showed you in here, if it can't produce belief maps that look exactly like this, then I will again punish the neural network again. Same thing goes for each output for each cascades. As a result, in here what the authors did is that they trained the model or force the model to learn to predict these belief maps starting from the output of cascade 1. As a result, every time the cascade 2 gets the output of cascade 1, it already has a estimate of the predicted location of my vertices and centroid. Same thing goes for the affinity maps. So in affinity maps, we will be monitoring in the loss function not only this output, but also output from here, 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 and here. So these 16 feature affinity maps, for let's say that for cascade 1, if it fails to detect the affinity maps that look exactly like this, that as an example in here, if it fails to predict an affinity maps like this, I will penalize the neural network the same way I will penalize the network if it fails to detect the affinity maps or recreate the ground truth affinity maps in this section. As a result, I have sort of a very nice gradient flow like GoogleNet, that I'm injecting the gradients in these cascades. So these are not like ResNet connections that they have residual connections. So, and this is in total 92 layer, approximately 92 layer deep convolutional neural network. So you would need sort of gradient injections to get it to train nicely, and this is sort of in a way working as gradient injections, that you are calculating the so all these functions come up to this in here in the loss function, and all these come up to this in here for a loss function for belief maps. Loss function for belief maps and loss function for affinity maps. I'm simplifying the entire loss calculation in here just for presentation purpose, but this eventually works almost the same way. So I am calculating loss for the belief maps, I'm calculating loss for the affinity maps, and then I'm passing on the gradient along these lines. So as a result, I'm having a gradient injection. Same thing goes in here. I'm passing the backward gradient flow along these chains. As a result, I can train these neural networks much easily. Now I would go into a little bit more details about each of these individual cascades. So each of these individual cascades in here, for the first cascade, for both the chain, they will have 5 convolution layers. For the second, starting from the second to the sixth, they will have same number of convolutional layers. They will have 7 convolution layers each. Same thing goes with the affinity maps, 7 convolution layers each. As a result, you end up with about 92. So in here you in this parts you only have 12, 10 in here, 2 in here, and you have for the cascade 1 and cascade 1 from both chains you have 10, 5 plus 5, and in here you have 10 blocks each of size 7, so you have 70. That makes up 80. So and you had 12 in here, so that's 92. So you have about 92 you have 92 convolutional layers in here to train. That's a lot of parameters to train, and that's why DOPE is very hard to train. And the original authors, as far as I remember, they use a DGX NVIDIA DGX workstation with A8 V10s V100 GPUs or something like that. So it's a very expensive, very fast workstation, and obviously I could not create that with my setup, which has only 2 GPUs. So later on in the next videos, I'm going to talk about how I plan to modify this architecture just for learning purpose as well as for the project. So that's it for this video. I hope you liked it, and please let me know if you have any question. Thank you.